All right, welcome back. If you watched the last video where I explained the procedure for doing Newton's method, I recommend watching the video I made called, I don't know what it's called yet, I haven't made it yet, but about the Newton's method equation and going through it and solving it, because that will be a much better explanation than the one I provided last video, because last video is kind of all over the place, and I apologize for that. So if you're still confused about the equation we got for going through Newton's method, watch that video, and that should do a better job explaining it. All right. Without further ado, let's keep going through the material. All right. Let's talk about the failure of Newton's method. All right. If in one of your steps the point has a derivative of 0, its linear approximation will never intersect the x-axis. So then Newton's method will fail.
Okay.
Once you get there, there's no going back.
Yeah.
Sound good? That makes sense?
Hold on. Okay, yeah, that does make sense. I'm like looking at the graphs, that makes sense.
Yeah. If I started with this point for Newton's method and I made a line, it's never going to intersect the x-axis. So, like, how can I keep going?
Yeah.
I won't approximate my root at all. My root at all.
Yeah.
Okay. So, additionally, sometimes Newton's method may fail to converge at all, and convergence is a thing we'll deal with later. But all it means is get closer to a solution, right? With our example, when we did the x squared graph, you could see that that Newton's method got us closer and closer to the x value we wanted. But here, using Newton's method doesn't get you closer to the root we want at all, right? If we start with this point, we use Newton's method, the next point we get will be this point. When we use Newton's method at this point, the next point we'll get will be this point, and that's where we started. So it just goes back and forth and back and forth. So sometimes if your original approximation isn't good enough, it might fail to converge to any good number or get closer to the solution you want. And this graph is a good illustration of that.
That makes sense.
Okay. Additionally, if a function has many roots, it is possible that Newton's method will find a root you were not looking for. Let's say I used Newton's method to try and figure out what this root was, all right? And I picked this point. It's too far away. Newton's method will end up bringing me over here, which will then bring me over here, which will then bring me over here. It's converging to this root. You see you see how that's happening?
I do see how. Yeah, exactly.
But I was looking for this one. So because my original point approximation, the point I chose was not a good guess for the root, it ended up finding the root I didn't want. So that's why step one, picking a reasonable guess, is actually really important. Yeah.
Okay, that makes sense.
Cool. All right. Any questions on that?
No.
Those are the three instances where Newton's method may fail. So
okay.
Just be super.
Yeah, those make perfect sense.
Yeah, and they can just be, and yet again, you can bypass them just by making your first guess like a good guess.
Yeah.
So that's why step one is actually more important than you think. Pick a reasonable guess, otherwise it might not work.
Okay, cool.
And also your first guess can't be a point where the derivative is 0, because otherwise then you'll have a flat line that never intersects the x-axis. Right. Differentials are, I don't want to say stupid, but they're the natural continuation of what we already talked about. It's just a different way to write derivatives. In the past, we've written derivatives as dy over dx equals the derivative.
Okay.
A tiny change in y divided by a tiny change in x equals the derivative there. So you can write this in differential form by multiplying both sides by dx and saying that a tiny change in y equals the derivative times dx.
Okay.
That's all differential form is. It's just writing the derivatives that we all know and love in a different form.
Okay.
Cool. We cool with that?
Yeah. What would why would someone do that?
I'll explain in just a second. So.
Okay. Cool. Sorry. Keep going.
Yeah, I'll explain later, and we'll do a cool example of it later. But this is important because it tells you a tiny change in y as a function of our x and dx. It tells you what your tiny change in y will be if you know what your x is, because then you can find the derivative, and you know what dx is. Given they have to be really small, otherwise, it's not a good approximation. Okay, cool. So that's why it's useful. We call this the differential. It's the differential of or differential. Okay, we call this the differential dy, and this the differential dx.
Okay.
Just mathematical notation.
Yeah.
So when you see this, you should just basically realize, oh, it's same, the exact same as this. We're just multiplying both sides by dx.
Mm-hmm.
All right. So the textbook basically said the same thing. If a function is differentiable, then we can write dy equals f prime of x times dx. Because if it's differentiable, we can write dy over dx equals f prime of x, and we can multiply both sides by dx.
Yeah.
Okay. dy is dependent on x and dx. You can see that. The value of dy depends on whatever x is and what dx is.
Yep.
And sometimes we write df instead of dy. They mean the same thing.
Okay.
Because, y and f of x, y and f, same thing. So sometimes we write df instead. It's the same thing. Right. So derivatives and derivative formulas can be written in differential form. And we're going to go to Jamboard very quickly to illustrate that. All right. So I'll just illustrate the concept very quickly. If we're looking at x squared, we would write dy over dx equals 2x. If I want to write it in differential form, I would write it as dy equals 2x dx.
Okay.
Does that make sense?
Yeah.
Cool. So for example, if I asked you to transform this into differential form, you just write this. Does that seem pretty straightforward?
Yep.
Okay, cool. We can also write our derivative formulas in differential form, right? We said that, let's do our sum rule, right? The derivative of the sum of two functions with respect to x equals the derivative of the first one with respect to x plus the derivative of the second one with respect to x. I don't know if you remember a long time ago, I talked about how we use u's and v's, and I hate it. This is exactly why.
Yeah.
But this is just the sum rule written in Leibniz notation. The derivative of a sum is the derivative of the first one plus the derivative of the second one.
Mm-hmm.
We can write it in differential form, right? Because in this case, y equals u plus v, right?
Yeah.
So then if we want to make it in differential form, we have to get what du plus v on its own, because that's dy in our case. Because the function we're looking at is u plus v. So getting this in differential form, we have to get du plus v on its own, because that's the dy in this case.
Yeah.
All right. So to do that, notice how we can just multiply both sides of the equation by dx, and all of the dx's will go away.
Mm-hmm.
So this is the sum rule in differential form. A tiny change to u plus v equals a tiny change to u plus a tiny change to v. So this, we would say, is the sum rule in differential form.
Okay, yeah, that makes total sense.
Okay. Additionally, the product rule tells us that the derivative of u times v equals the derivative of u times the second function plus the derivative of v times the first function. If I want to get this in differential form, I multiply both sides by dx, and I get du times v equals du times v plus dv times u. This is the product rule in differential form. Because I multiply both sides by dx, I got the dy on its own, because the dy in this case is the product of two functions. And then when I did that, I would get the thing I want in differential form.
Yeah.
Cool. And I still don't understand what was going through Leibniz's head when he decided to use u's and v's. But here we are.
Yeah.
It's gonna get worse. There's a formula when we do integrals with u's and v's that I hated. I might even just use different variables, if I'm being honest, because I really do hate them that much.
Okay.
But
who's to say we can't just use two different letters?
Yeah, who's to say that? We'll invent our own calculus. Okay, does that concept seem good?
Mm-hmm.
Cool. I was a little too excited when I made this last night, so I decided to write this in all caps. I guess I'm really excited to teach things. All right, this is what I was talking about earlier with Henry, and I'll explain again for YouTube. If we have a line, the slope is the same everywhere. So when we calculate the slope as delta x over delta y, delta y over delta x, which is the rise over run, it doesn't matter what 2 points we use because the slope is the same everywhere.
Yeah.
Using the fact that the change in y is divided by the change in x equals m, we can figure out what a change to our y coordinate will be if we know how much we are increasing or decreasing our x coordinate. What I mean by that is we have a line. We know that delta y over delta x equals the slope. So then a change in y will be the slope times whatever change in x we choose.
Yeah.
If I'm looking at a point here and I'm looking at another point here, if I want to find how much y changes, I take how much x changes and multiply it by the slope.
Yeah.
Using this equation. All right. And remember, this equation only works for lines.
Okay.
Right? Because remember, our slope definition only really works for lines.
Mm-hmm.
So when we write dy over dx equals the derivative there, right? That's basically a line formula. It's basic because remember, when we use dy's and dx's, we're basically saying, well, as our change in y's get infinitely small, our function looks like a line. So we write this because it is a line when it's infinitely small, right? But whenever dy and dx are any value that's not infinitely small, we're not going to get a perfect line. All right. So what this really represents is the slope of the tangent line to a function at that point, right?
Okay.
Because as we zoom in far and far, the function becomes indistinguishable from its own tangent line. So if we calculate the slope using a tiny change in y and a tiny change in x, we're calculating the slope of that tangent line.
Yes.
Does that make sense? So if I used this formula to find a change in y of our function, I wouldn't be finding the change in y of our function, but I'd be finding the change in y of our tangent line. Because this describes our tangent line, not the function itself.
Okay.
The reason we can say it describes the function is because if it's infinitely small, then the tangent line and the function are the same.
Yeah.
But this equation is just really describing our tangent line. So if I use this to describe a change in y, I'm not finding the true change in our function. I'm finding the change in our tangent line. All right. Okay. So if I used f prime of x dx to find the change in our function, I'd really be finding the change in our tangent line.
Yeah.
Does that make sense? But the point is, if our dx's are really small and our dy's are really small, the tangent line is a really, really good approximation of the function.
Mm-hmm.
So I can still use dy equals f prime of x dx as long as my dx's and dy's are small enough. Because then it'll be at least a good enough approximation.
Okay, yeah.
Does that make sense? So yes, that's one of the uses. That's one of the uses. It's that, let's say we're graphing like how much blood is in my heart as a function of time.
Mm-hmm.
And I want to figure out how much does my blood change over a tiny fraction of time.
Mm-hmm.
I could use this equation, right? My blood is going to change, the tiny change in my blood is going to be the derivative of the function at that point times whatever the tiny change in time is. I'll do time. All right?
Yeah.
Because even if our function's some really curvy thing, all right, as long as our changes are super tiny, the tangent line approximates the function almost perfectly. So we can find approximately what the tiny change in my blood is going to be if we're evaluating tiny changes in time.
Yeah.
All right. This is actually what car speedometers do, all right? Car speedometers, they measure how fast you're going at a certain instant, right? But how they do that is they measure the distance you traveled and divide it by, they measure a distance you traveled over a very small amount of time, all right? Mm-hmm. And so like, let's say you travel 0.2 meters over 0.00001 seconds, all right? They'll say then your velocity there is whatever this number is, right? Distance over time.
Okay.
Right? What they're doing is, let's say your position looked like this, right? Is they're calculating the slope of your function using 2 points really close together.
Mm-hmm.
That's kind of the same thing I explained it poorly. That's kind of the same thing here. If you use points that are really close together or changes in y's and changes in t's, just like how your car speedometer uses a really small change in t, it's going to approximate perfectly the derivative and your velocity or whatever you're looking for.
Yeah.
So to show a real life application of that, car speedometers, they use this approximation, and the idea that this approximation is really good if your dt's and dy's are small enough to get your velocity, and your velocity obviously is accurate when you're in a car. Like, it's obviously telling you how fast you're going. So that's a real life application. Any questions on that?
No, that makes sense.
Cool. I'm glad it does.
Cool.
Okay. So let's review what this slide says, and it's kind of what I said before. When it comes to derivatives, things as we have seen are a little bit more tricky. Although a function looks like a line if we zoom in far enough, it doesn't truly become a line unless we zoom in infinitely far. This analogy is similar to how we may perceive our immediate location on Earth as flat, but there's still curvature we cannot perceive. Only if you zoomed infinitely far into the Earth would it be truly flat at the location you zoomed into. This is the analogy Henry and I came up with before. As a result, when we say dy over dx equals f prime of x, dy and dx are infinitely small quantities because they have to be if our function is to be truly linear at our point of interest. If we try to calculate dy using a finite number for dx, the change we get will be the change of the tangent line experiences, not the function, and we just described that. However, we've discussed that the tangent line is a super good approximation of the function if we stay close to the point of interest. As a result, we can calculate small changes to dy, or small changes to y, dy, with small values of dx, and our approximation will be phenomenally accurate. This is an incredibly useful tool. Any questions on that?
Perfect.
Cool. Right. Yep, this is the same thing. Estimating change with differentials. If we know the value, this is the exact same thing we said before. We can estimate small changes with differentials by noticing the change in the function is the derivative times the change in x.
Cool.
Make sense?
Yeah, that definitely makes sense.
Cool. This is just some terminology that the textbook, you can just take a picture if you don't want to take notes on this. But this is just some terminology that the textbook wants you to know. There's different ways to describe change. Change of functions, that is. There's absolute change, which tells you the exact value that your height or your y coordinate has changed. We call that delta f. Relative change is your change in f divided by whatever the function was at that point. We call it relative change because you'll get a fraction, and it'll tell you how big the change in your function was relative to whatever the original height was. If your change is small relative to what the function was before, then you'll get a small fraction. So it tells you that the change, relatively speaking, is not significant because the function was originally very large and the change is very small.
Okay.
Cool.
Yeah. Yes.
And these are just estimations, right? The change in f can be approximated by df if our values are small enough.
Yeah.
So this is the true thing, and this is the estimated thing we get from using small values of df and dx, which are really good approximations if they're small.
Okay.
Percentage change is just the same is the same thing as relative change, but as a percent. You'll get a fraction. You multiply it by 100. That tells you the percent. The percentage of the original function that the change was. Let's say your function changed by 2, and originally the function was at a value of 8, a height of 8. Then you get 2 divided by 8, and you get 25%, which means that your change was 25% of what the original function was.
Yeah.
That's why we call it percentage change.
Okay.
Cool. Any questions on absolute, relative, and percentage change?
No, that makes sense.
And the difference between true and estimated, right? The true thing is you just have to figure out what the change in the function is. We can estimate it, though, by using our DFs and stuff.
Yes, exactly.
Cool. Last one. Actually, I didn't realize we're already at the end. Related rates problems. Last thing, and then you're free to go. Related rates problems allow us to figure out how things change in relation to one another, right? For example, let's see how the speed at which a sphere's volume changes. Let me say this, and I'll do the example in Jamboard. It'll be easier to see. Let's see how the speed at which a sphere's volume changes is related to the speed at which its radius changes. All right. Okay. So let's say you had a balloon, and it was a perfect sphere, and it was deflating. The rate at which the radius of the balloon decreases obviously is correlated somehow with how the volume is decreasing, right? Yeah. And related rates problems, we can figure out how they're related using the idea of related rates, and I'll show you what I mean by that. So the first thing we do is, let's say we're asked, how does volume change with respect to time? All right. Here's what I do. I know that the volume of a sphere is 4/3 pi r cubed, right?
Yeah.
And I'm trying to answer the question, how does volume change with respect to time? What happens if I apply the derivative operator with respect to time on both sides? What do I get? What do I get on this side?
Just the derivative of b.
Yeah. So if I do implicit differentiation, but the derivative operator I apply is with respect to time, then on the left-hand side, I'm going to get dv over dt. Isn't that the derivative of volume with respect to time?
Yeah.
Doesn't that answer how volume changes with respect to time?
Yes.
Cool. So if we just do implicit differentiation on this right-hand side, we'll get how the change in radius relates to the change in volume.
Okay, cool.
Cool. So all we have to do is the chain rule, right? So we have to do the same process we did for implicit differentiation, all right? So all right, we're trying to find the derivative of let me backtrack. We're trying to find the derivative of 4/3 pi r cubed with respect to time, right?
Yes.
The chain rule tells us this is going to be equal to the derivative of 4/3 pi r cubed with respect to r times the rate of change of r with respect to time.
Yeah.
That's what the chain rule tells us.
Yeah.
You agree with that step so far?
Yes.
We can find the derivative of this, right? Because the variables are the same. It's just the power rule. We know how to find the derivative of this with respect to r, because our only variable up here is r. Everything else is a number. Pi is a number, 4/3 is a number, whatever.
Yep.
So this is a function of r. If we want to find the derivative of this with respect to r, the variables are the same, so we know how to do that. We just apply our derivative rules.
Yeah.
It's going to be 4/3 pi times whatever the derivative of this is, which is 3r squared, right?
Yep.
So 4/3 times 3 means the 3 is going to go away.
So then it's just 4 pi r.
Pi r squared. We have to, when we do the power rule, we take 3 down.
4 pi r squared. Yep.
All right. Times dr over dt.
Okay.
Yeah. Yeah. So then we could say, we could write this as our answer. All right. We've now related how quickly volume changes with how quickly radius changes using implicit differentiation.
Cool.
Isn't that what we wanted to do? We wanted to ask, how does volume change with respect to time, and how is that related to how much the radius changes?
Yeah.
And also, the rate of change of volume depends on what our radius is. You'd expect that to be the case. What I always recommend you do is when you get an equation, make sure it makes sense. The rate of change of volume depends on what our radius is. If our balloon is super big, obviously the volume is changing a lot with respect to time, right? Because if you deflate a very big balloon, the volume changes very quickly. If you deflate a small balloon, the volume isn't changing as quickly as if the balloon were very large. So you'd agree that then when we see that we have an r here, it makes sense. Because the bigger r is, the bigger the rate is, and that's what we would expect to happen.
Yeah.
Additionally, the faster our radius is changing, the faster our volume is changing, right? If dr dt is big, then that means dv dt is big.
Yeah.
And that's what we'd expect. So just from using common sense, we can look at this equation and go like, yep, this makes sense.
Okay.
All right. Any questions on that?
I don't think so. That makes sense.
That makes sense. So this class of problems are called related rates problems.
Related rates. Okay, cool.
And you can see why. We related the rates dv dt and dr dt. And can you see that all it really is just implicit differentiation with, instead of ddx, use ddt. So it might seem complex at first, but it's nothing truly groundbreaking. It's just implicit, like we were doing before, with ddt's.
Yeah.
Cool. And the thing is, let's say I was given a problem. That asked, and this is the last thing before we disembark. How much time do I have, by the way?
It doesn't say. So
okay, so
at
yeah,
least 10 minutes, I think.
Yeah,
I think it usually starts at 10 minutes.
Yeah. Okay, so let's say I was asked a problem. How, at what rate is the volume of a sphere changing if the radius is changing at 2 meters per second and the radius is 5 meters. Before we did that problem, you'd be like, how the hell would I solve that, right?
Yeah.
But with our answer, we found an equation for what the rate of volume is, right? dv over dt. And it equals 4 pi r squared times dr over dt. And the problem tells us the radius is changing at 2 meters per second. So dr dt is 2, right?
Yeah.
It also tells us the radius is 5 meters. So we can replace the radius with 5. Now we no longer have any variables in it. So our answer is going to be 4 pi times 25 times 2. And this will tell us the rate at which volume is changing. Okay. Any questions on that? It's a complicated process, but hopefully you understand the intuition for it.
That does make sense.
Cool. So there's a strategy for related rates problems. Most related rates problems will look like this. It'll ask you at what rate is something changing. All right. So when you see that, you're like, I want to get that thing on its own. For example, in this question, if we hadn't done what we did before, and we asked at what rate is the volume of a sphere changing, all right, I could go like, well, I know the volume equals 4/3 pi r squared, or pi r cubed. Write an equation for volume, and then apply the derivative operator to both sides that will tell you the rate you're looking for. Obviously, applying ddt to both sides will give you dv over dt, and that's the rate you're looking for.
Yeah.
So the general strategy is, if you're given a related rates problem, write an equation relating the thing you're looking for to something else. We're looking for the rate of change of something, and we might not know an equation for that yet, but we at least know how the volume relates to radius, right? So if we want to ask how does the rate at which volume changes depend on other things, we'll do implicit differentiation to get dv dt equals this.
Yeah.
Cool. So I think I outlined the general process for solving related rates problems, and I'll go through that in a second. But is the general premise of related rates problems kind of making a little sense?
Definitely, yes.
Cool. All right. The general strategy for solving related rates problems. Understand the problem. Identify the variable whose rate you seek and the variable whose rate of change you know. So in the first example would be like, I'm looking for the rate of change of volume. I know the rate of change of radius, and I know what value the radius is. So ask, what am I looking for? What do I know?
Yeah.
Develop a mathematical model of the problem is the second step. Well, first of all, if I'm given the radius, that's like alarm bells are going off in my head, because I'm like, I know an equation that relates volume to radius.
Yes.
So I know where to start.
Yeah.
All right. So look at what you want to know, look at what you know, and think about if you know any equations that relate those kind of things.
Yes.
And I'm like, I know that volume equals 4/3 pi r cubed. So that's my starting point.
Okay.
Develop a mathematical model of the problem. All right. Write an equation relating the variable whose rate you seek with the variables whose rate of change you know. That's like us writing v equals 4/3 pi r cubed. Then you differentiate both sides implicitly with respect to time. Okay. We apply ddt to both sides. You do your calculus, you apply your derivative rules, and you'll get your answer. We got dv over dt equals 4 pi r squared times dr over dt.
Yeah.
So the last step is just to substitute the things we know. We knew what dr dt was, and we knew what the r value was. So we substitute those in, and we'll get a number for dv dt,
Yes.
which is what we were looking for in the first place.
Yeah.
Then the last thing you do is interpret the solution. Let's say we got 100 as our answer. That means that the volume of a sphere is changing at 100 meters per second.
Dang. Okay.
All right. And we did a textbook practice problem just then.
Cool.
Any questions on related rates?
No.
Cool. Hopefully you can see it's not, even if it sounds complicated, it's just implicit in disguise.
Yeah. No, I can see that.
All right, cool. So it's not too groundbreaking. That's all of Unit 4. Woohoo.
Wow.
I hope you have an amazing day. That's it for today. For YouTube, that's it for today. I'm going to end the video, then I'm going to talk to Henry individually. But that's all Unit 4. Next week, we start talking about integral calculus, which will be really cool. So I'll see you guys in the next video. Have a good day.